Hi, in this video I will present you some ideas on the design of an encoder. Uh, One of the standard blocks that we are studying in project P2. Alright, so here I've got a whiteboard with some details that I would like to commend you. Starting from the specifications, the symbol, the truth table, right? The indications given with these specifications, and then some details about the inputs and the outputs that you can conditionate for this chip. And finally we will draw a sketch of a timing diagram. In this way we will get a picture of what is going on with the circuit, that in a continuation we can design as usual following several different plans. For example, we will try to get the equations. We may like to transform the truth table as it is exactly into VHDL, that is the plan B. Or instead we may like to build this encoder using encoders of the same kind but with less bits, right? Something like this, like plan C2. So this is the idea, right? So let's just start this way with a symbol. And here you are what we like to design this time. The symbol, or an encoder of 10 inputs to 4. So this device is for converting the code that you get from clicking keys, from any kind of keyboard. Okay, you may imagine 10 keys from a mobile for a phone device. You see, you have a keyboard here, so you have some keys. So the idea is that when you click a key, you get some kind of binary code. So that's the idea, for example, of an encoder. You can have 10 keys, 6 keys, or 20 keys, or a full keyboard from a computer. It's all the time the same idea. You have a lot of keys like in this keyboard, and the idea is all the time the same. What kind of code you are going to get when you are clicking a key, or something else. Naturally, what happens, for example, if you are clicking 2 keys at the same time? What is the behavior of the circuit when this kind of thing happens, right? So naturally it is better to start not with 20 keys or 100 keys, but just with 10 keys, for example, right? By the way, this circuit is just that standard that has been here in the commerce for forever. It's the typical standard circuit that is named like this, 74, for example, LS, to give you this logic family, low power Schottky TTL, and the reference number is, for example, the 148 or the 147. You see, the 147 is precisely the encoder 10 to 4, while the 74LS 148 is the encoder 8 to 3. You see, 8 inputs, 3 outputs. So that is the function of the circuit, to convert from the code that you are inputting the circuit when you are clicking a key to binary, for example. That is the typical situation, all right? But the circuit, as usual, has some extra keys to control how it behaves. For example, enable input and enable output, and another one that is in this chip specifically, that is called group select. So let me show you how these signals may like to work, right? And that is the situation, for example, that we can go explaining very well from the table that has been, you see, previously writing down here in the whiteboard. So you have the table. In the left side there is the inputs, and on the right side there is the 6 outputs. You see, group select, the code, and the enable output, while in the left side you have the keys that you are clicking, the 10 keys, and the enable input in this side, right? Inputs, outputs. Let's consider that the keys are packed together, just to go trying things like this every time that you have a different chip. For example, this time, let's consider that the keys are packed together into a vector form, like the output code. You see, you have Y3 down to 0, just to represent different binary codes from the 0000 up to 1001. That is the code that you get when you click the number 9. All right? So if you click the number 9, the function of the circuit, like here, when you click the number 9, is to generate the 1001 code in binary. That's the function of the circuit. So, but let's go step by step, because here you have, for example, some differences that I have to comment. The idea, for example, that is always possible to use active high or active low inputs to define how the circuit behaves, right? For example, and that is very appropriate here because we talk about keys. And if you have a key, you can connect the key this way, for example, or that way. You see, it's the same circuit. So you can connect the resistor, the voltage, the power supply. So the VCC, for example, is 5 volts. This is a resistor to fix a value here, and then there is the push button that you can click or not. So you click or you press the key and you release the key. So in this way, if this is the circuit that you are proposing, what you've got here is this equivalent, and this means that when you are pressing the key, okay, like now, I'm pressing the key, I'm generating an electrical contact, so when I'm pressing the key, I generate a 0. So you see, the action is that one of pressing the key. So what kind of digital code you get when you press the key? Because of this circuit that we will call active low. Well, a 0. That is why we call that circuit active low, right? And on the other side, when you release the key, you see, if you are not anymore generating an electrical contact between these two metallic parts, you see there is a straight connection of the output key L to the VCC. So the code that you generate is a 1. So key L is 1. So you see, key L is 0 when you are pressing, and the other way, key L is 1 when you are releasing. And this is why you have this name as well. You see, key L, and the L means active low, all the time here in this digsys course, introductory course on digital circuits. This is what we do all the time. If we would like to emphasize that in a given circuit, when you are pressing, or you are just realizing this digital action, whatever it is, this time is pressing a button, and you have to emphasize which is the code that you generate, and that code is a 0, you label the key that way. Key underscore L, meaning low, right? So the things will happen when 0. And here you have the same circuit, but in the other way. Look at this, the same key, but now the key is positioned, you see, is connected between the VCC, the 5 volts, and the 0. In this way, when you are clicking, what you get is a 5. That's it, a 1, you see. So this circuit, you see, it's very similar, but it's just the opposite way. When you click, you are generating a contact, and now what you've got is a 1. So this is why the name of the digital signal associated to this circuit is key only, instead of key underscore L. And that may be, you know, a key or a button, doesn't matter. You see, a button, it may be a button or a switch, it doesn't matter. It's the same idea of generating a digital voltage to be input into the circuit, to make some processing from these logical values. That is the way it works, okay? And that idea is also possible from the output point of view, right? For example, here you are representing the output code. Y3, Y2, Y1, and Y0. So this means that this is an output, a digital binary output code, active high, because you know it's Y, not YL. It's Y. So this means that if you are clicking a 9, what you get is 1001, not just the opposite value. All right, but look at this. You have, for example, a signal that is named GSL. You see, instead of GS, you have a signal that is named GSL. And so what is the meaning of this? Well, the meaning of this is that, for example, if this signal has to be activated for any reason or because of the table, for example, this time, for this input combination, this signal is activated, the value that you get to represent, to emphasize, to note this activation is a 0 because the name of the signal is group select active low. All right, and here you see, because it is Y and not YL, the code that you get is the right one, active high as usual. You see, for example, the 1000 is representing the number 8. Okay, and that is not a problem because if you are pretending, for example, lighting a LED when this signal is active, this time active low, you know very well that you can connect this signal GS active low that generates a 0 when active. You see, a low voltage, you can connect it to a LED just in this way as a common anode connection. You see, we have studied that in another video, in another lesson. You see, so that is not a problem, because if you have a low voltage here, when you like to have light indicating that this signal has been activated because of the truth table, you see, in this way, when you have a 0, the current is flowing from the VCC, that is 5 volts, so it is a 1, down to a 0. So the current is flowing through the diode in the right way. You see, biasing the diode in a place, you see, in a point on the curve from ID to voltage anode to cathode, in a place where some current is going through the diode, and in this way you have light. You see, the diode is emitting light this way. And you know that from this circuit you have this design equation. You see, the value of the limiting resistor is, you can got that equation from the analysis of this simple electrical circuit. And so RL is the VCC minus the voltage anode to cathode minus the VOL, but in the worst case scenario. So for example, VOL maximum, you see, and that, for example, for a TTL circuit, if this is what you have here, a TTL circuit, you know that is 0.5 volts. Okay, the circuit is generating a 0, but it's not 0 volts exactly, but 0.5 as the maximum. So that is the worst case. You see, so you can consider these values here, the voltage anode to cathode in the bias point, and the same as the current that you like to get in the bias point. For example, 5 milliamps and 1.8 volts. You get this data from the data sheet of the diode that you are soldering here at this output. So from this equation you get the resistor, for example, this time 540 ohms or something standard, 560 ohms, right? So that is the resistor that you have to connect to an output that may be connected this way to, it is, active low. So well, from all these considerations that are something electrical futures, you can start talking about the circuit. Just imagining what it has to do. For example, this is the typical enable, even if it's active low, you see, no problem. So this means that when this input is 1, doesn't matter if you are clicking keys. You see, if this input is a 1, this means that the circuit is disabled. So the output of the circuit, you see, we are copying here the truth table of this circuit, the 74LS148. So this is what the manufacturers usually do. You see, if you are disabling the circuit, what you get is 1, the code 0, and 1 here. You see, the output enable is also 1. So that is the disable condition. This is the set of output. That means that the circuit is not in action. It's passive, completely off. But if you enable the circuit, it may happen, for example, in a circuit that is driven like this using active low circuits connected to keys that no one is pressing any key. So if no one is pressing any key, you have ones everywhere. So that is what you've got here. Ones everywhere because no one is pressing any key, right? So if you have got 0 here and ones everywhere, the output of this circuit is like this. Group select is yet 1, is still 1, and the code is the same, 0, 0, 0, right? Because it has to be some kind of code. And the enable output this time happens to be 0. That is the condition that means no key pressed, okay? You are not clicking, you have the circuit activated, this is your device, it is working, it is not disabled, but you see, you are not clicking any key with your fingers. So this is the set of outputs that you get from the circuit, all right? That one, 1, 0, 0, 0, 0, 0. And then, you see, you are repeating 2 times the same code, 0, 0, 0, 0 and 0, 0, 0 for 2 different situations, but there is yet another one where you can get the code 0. And when this happens, for this kind of encoders, this happens exactly when you are enabling the chip and you are clicking exactly not a single key but the 0. You see, if this is what you do, if you are clicking the 0, you see what you get is a 0 now. So this is the full set of inputs, 1, 1, 1 everywhere except in this data active low 0. Here is where you get a 0 because you are clicking the key 0. You see, this is the action that you are pressing the key 0. So in this situation, you get again the same 0, 0, 0 because this is now the code of the key that you are clicking, the key 0, right? All right. But in this time, what you get is enable. The enable output law is not active like when it were disabled, but now group select happens to be 0. You see, that is the difference. You see, the code repeated 3 times, but you see, 3 times means that you need 2 digital values to determine what is happening here. When you've got 1, 1 disabled, when you've got 1, 0, no key pressed, but now you have 0, 1, right? And 0, 1 means that you have 0, 0, 0, 0 as the output code, but because you are clicking the key 0. That is the situation. So that is the group select for. It is going to be 0 every time that you are clicking any key, whatever, right? So that is the function of the group select. You are selecting one of the keys, so that is why you get a 0 this time, because it's active low, right? So that is what happens, for example, when you are clicking the key 1. So if instead of the key 0 you are clicking the key 1, okay, what you get is the code 0, 0, 0, 1. This means that the key 1 is pressed, and the conditions that you've got here are the same. Group select happens to be 0 because you are clicking the key 1, and the enable output is deactivated that way, right? And something else, because you know, if you are clicking the key 1, you can also go and click the key 0, right? So here you have to choose something, and the people has designed that chip all the time choosing priority high, and this means that if several keys, you see, if several keys are pressed simultaneously, the circuit will give you only the binary code of the greater number that is decoded. You see, this that is encoded. You see, the greater number that is encoded in some way, right? If several keys are pressed simultaneously at the same time, only the binary code of the greater number is encoded. Okay? That way. So this means that you are pressing the key 1 and you are pressing the key 0 or not, you see, you have a 0 and you have here, doesn't matter. Because if you are pressing the key 1, what you get is a 1. That is why you've got an X here. And that happens again, you see, if you are enabling the chip, you are not pressing any key, but the key number 2, you see, and then the other 2 doesn't matter, because what you get is the code 0010, which means, you see, this means that you are pressing the key 2, all right? And that way, all the time, down to the number 8. So if you are pressing the number 8, Doesn't matter if you are pressing at the same time with all your fingers all the keys, the 7, the 6, the 5, because the number 8 is the greater number that you are pressing, you get the 8. All right, and finally, the number that has more priority is the 9. So if you are enabling the chip and you are pressing the key number 9, that is going to be the case. You are clicking a 0 here because you're generating 0 and 1, 1, 1 everywhere else. So if this is the input of the circuit, doesn't matter if you are clicking now several other keys, because you are clicking the 9, what you get is the code 1001 and group select activated and 1 in the enable output. So that is the truth table that we plan to design in whatever plan A, plan B, or plan C2. And you have to realize now that you have a lot of don't care, you see. This is, as you know, a don't care term. Doesn't matter if you click or not the key, all right? So because you have a lot of combinations of such type, don't care, the truth table is that long, you see. You have 11 inputs here. So this table that we have represented that way, that short, you see, indeed, it is that long, 2 raised to the power 11, so 2048 different combinations. So logically, if now we have to go attacking the circuit, for example, using equations, it is not going to be possible to write now the 6 output functions by definition using the canonical factors, because you know it's impossible. Perhaps some output is going to be right. For example, this one, enable output active law, is rightly written using maxterms, because you have a single maxterm and then you have 2047 minterms. So that is easy, but not the other one, right? In general, you have here a mix of everything, and well, you have hundreds of thousands of maxterms or minterms associated to the inputs, to the outputs. So it is better to do something else, like, you know, trying to copy the table into Minilog minimizer and trying to extract automatically the sum of products or the product of sums. So that is the way we will like to generate later on. You see, you will see that described in the digsys tutorial. You will find this table in Minilog, so that from this table you can extract very well the set of 6 equations that you will translate to VHDL, so that the architecture is going to be an structure of logic equations. The circuit to generate this encoding function. That is one way, and you know that the other way is going to be plan B, starting transferring this truth table directly to VHDL using, for example, a flowchart. Why not? You may start thinking here this way. If you see, if you know, by means of a process in VHDL, you can go and subdivide, as you see here with the green lines, this table in several sections and make it easy to write it directly in VHDL without having to care about the equations generated by the minimizer. Just trying to translate straightly away the table into plan B architecture. Or, as you will see in the example, you have this circuit already implemented in Proteus, and if you take a look to the internal architecture of this circuit, you will see that it's composed of 2 standard 74 LS 148. So an encoder 10 to 4 can be built using a smaller components of the same kind, using plan C2 interconnections, you see, and 2 modulos like these, encoders 8 to 3 can be connected together in some way and using some logic to develop this function of the same kind, encoding. So that is what we have in mind. So from these initial specifications that now we will accompany with a sketch of a timing diagram, you can indeed invent at least 3 different projects. One based on plan A, and develop it accordingly using the electronic design automation tools, and test it using a test bench. And then, if you like, a plan B project, and then if you like a plan C2 if you get if you find what you need, which is an internal architecture of this circuit built using smaller components of the same kind. All right. So before going to the planning section, you know that there is something like the timing diagram that is interesting to sketch, just to the idea of translating this static, this truth table in time. So like if you were in the lab, all right, and what is the meaning of this? Well, in the lab, or when you have this as a prototype, you can click the keys. You can click several keys at the same time. You can disable or enable the chip, and you can watch what happens with the output. So that kind of a sketch is very well written, drawn in a kind of a whiteboard or a sheet of paper. The only thing that you have to go here is, as usual, annotating in the same time scale, you see, where the time is the axis x. This way, all the inputs, for example, let's just start in this order. The enable input active low goes fast. And this means that we can invent now some kind of activity for the signal. For example, let's imagine that the circuit is active all the time, except from a period of time where the circuit is going to be inactive, like that. So this means that the circuit for all this period of time is going to be disabled, right? That is what we are pretending here. While when zero, enabled. This means that we are going to the circuit to go running correctly, like in this subsection of the truth table, right? Then what? Well, let's figure out here some activity from the keys. And this means that you also have to go annotating here the data active low 9 down to 0, right? Something like this. And you can represent that using 10 individual wires or as a block, all right? Why not? To save some paper here, we can do that as a block as well. This means that, for example, up to this point we have a combination, up to this point we have another combination of inputs, and here another one, and then another one, something like this. So what is that we like to go, inputting here to the circuit? For example, I don't know, a combination maybe here, for example, 0, 1, 0, 0, you see, we have to just generate a binary code of 10 different ones and zeros. So 0, 0, 1, 0, you see, 0, 1, 0, 0, 0, 1, 1, 1, 1. Then this means another one, right? Something like this. This is going to be the data active low 0, and this is going to be the 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is the data active low 9. All together conform this vector that has no meaning as a number, That is the point. Indeed, it means the number of keys that you are clicking, and in this specific combination, what I'm saying, you see, is that I'm clicking with my hand. For example, with 4 fingers, I am clicking 4 keys. The key number 9, the key number 7, the 6, and the 5. That is what I'm doing with this first combination, right? And that's all, because this is, several combinations of inputs. And so now what I have to do here, perhaps with another color, is to go annotating the different signals. For example, that belongs to the output side, the GS, the group selling, that way, okay? Then I can go and annotate as well the output code active high this time, 3 down to 0, and this is going to be a binary number, whatever it is. From 0, you see, when these circumstances are happening, or then 1, 2, 3, up to 9. No other output codes are possible here in this circuit. All right, for example, a code like 1010, it's impossible in this circuit because there is no combinations here. Of the 2048 of them, that is going to generate such a code as the 12 in binary, 1010. So the 10, right? 1010 is the number 10. There is no such key as the key number 10. That key do not exist, so this code is not going to be here. Perhaps if you have a different encoder, 16 to 4, covering all the binary codes with 16 keys, that is another thing. But this time, what you've got here is the possibility to translate to binary, you see, only 10 keys. So this is a kind of a BCD binary, you see, or a BCD code is what you've got here. So you've got the GS, the Y, and finally the enable output. So now you only have to go and figure out what is going to happen for several combinations. And the first combination is very clear. You see, you get now a vertical line, because for all this time, you see, for all this time, the input signals are static, are having a given value, you see, and the value is enabled, the circuit is enabled, and you are inputting this value. So what you get here? Right, you get naturally group select, because you are clicking keys, you see, you are getting a 0 here, because it is active high. And then what? The code that you get now from this combination up to this point is the number 9, naturally. Okay, you get the number 9, because this is the key 9 pressed. You see, from the very beginning, you are just representing the signals in time. And from the truth table, you know what is going to happen here, and you start annotating comments and excusing the picture like that, right? So 0 in the group select, because some keys are clicked, and every time that you have some key clicked, you have a 0, and group select goes down, you see that way. And then the enable 0 active L, that is the opposite of the other one. You see, it has to be 1, right? Not active, that way. So this is what I'm advancing here, that the test bench will generate for me while simulating this input. All right, and then what? Well, something else like this. Up to this point, I've got a value. Up to this point, I've got another value. Up to this point, another value, and then the signal are going to be static this time, and then forever, because nothing else is going to change. So you see, this is what we call here, inspecting this sketch, this is what we call here the minimum time in this picture, where the signals are fixed, you see, because this time is a little longer, and this time is perhaps a double of this one. So this is going to be this minimum time. It is what we call the mean pulse duration, mean pulse, right? So now you can imagine the time scale, just to give this mean pulse a value for the next test bench in step 4 in the design process. So for example, mean pulse is going to be, I don't know, 1.2 microseconds. So if this is the duration that you are imagining for the mean pulse, this time, for example, is, I don't know, 4.7 times mean pulse, right? So that's not a problem. Referring every single time, this time here, if this is what you like to do later, this is, for example, 1.2 times mean pulse, right? This is what are you going to do in the translation of this picture into a test bench, right? That's it. So from this duration, you can imagine that you can run the simulation for example, if this is 1.2, I don't know, 100 or 200 microseconds. You see, that is the order that you have to give in the console of, for example, model sim simulation to get the full picture. So to finish the simulation sketch, you see, the timing diagram, you see, to finish this timing diagram, the only thing left is, you know, to get some values from the table and annotate them here. For example, if this is imagining when you are pressing the 9 and other keys, you can now simulate here that what you are doing is exactly, I don't know, for example, not pressing a single key. So you have that thing, 10 ones, all right, while this is yet a 0 because this enable input has not yet changed. The circuit is enabled, but this means that you are not pressing a single key. So you are representing this line in the this row in the function, in the truth table, right? So what you get naturally is very well known. It's exactly this code that you've got here. So this means that the group select is not going to be active that way, all right? The code for all this time while these signals are stable is just a 0, right? 0, 0, 0, and enable is because you are not clicking a single key is 0. That is what happens here, right? That is the correct. But now what happens next, you see, for another period of time, all right, is that you are disabling the circuit for a while, keeping the same vector as input. So now you are moving from this row in the table to the top one, right? Because doesn't matter any combination. So 1, 1, 1, 1 is also possible. What you are doing now here for this time is disabling the chip. So you see, you are in this row, and this means that what you get here is another period of time. Group select is 1 for this time, you see. The code is another time the same, you see, the 0 goes that way. And then in this situation, you are noticing that you are disabling the chip because the enable goes high. So this is what happens here, all right, up to this point. And now you can imagine another situation because now you see you are still disabling, but you can imagine, I don't know, that I'm clicking, for example, not the key 9, but 9, 8, 7, the key 6 only, right? Only the key 6. 5, 4, 3, 2, 1, 0. So that is what I've got as the code now. You see, I'm clicking the key 6. So what is that you are expecting? You see how it's not that complicated to imagine what is going to do the circuit. For example, doesn't matter now if you have changed this X, you see, because you are still in a situation for a while for these min pools where the circuit is disabled. So these codes are going to be kept for a while that way. You see, GS is still high, the code is yet a 0, you see, so this is what you've got here, a 0, and then you see, because this is a vector, 0, 0, 0, this 0 means, you know, 0, 0, 0, 0, you see, and the 9 means 1, 0, 0, 1 in binary. But you can represent that very well in binary, in decimal, because it's a BCD number, right? And then the enable is 1 for these min pools. And then what? You are enabling the circuit again, and what happens is that the input combination shows that you are clicking the key 6. So group select is going to be sensitive to that situation. You see it's going to be down or low, and the code is going to change immediately, you see. So now you will have a 6, and the 6 means 0, 1, 1, 0 in binary or in BCD, you see. And then the enable, because in this region of the table is kept high, right? It was high, and now in this region is kept high. So for all this time you've got this situation. And then whatever else that you like to test, you see, for example, let's test another situation where you have a 0, right? For example, if you like to test another situation where you have a 0, is that one. You have the circuit enabled, but now you are not clicking a single key, so you've got all ones except this. So this is the data L0 value, meaning that you are clicking the key 0. So what you've got from now on is the same group select activated. The code is going to change to 0. You see, you have a 0 here, and now you have another 0. all right? This time it was, because you are not clicking a key, you see, not a single key clicked, you see, but here you are clicking the key 0, so this is why you get the code 0 right now, right? And now you've got a 1, because even in this situation, you see that you are simulating, now you have a 1 here, so that is the point, okay? So that is an example of a sketch that can be, as you see, very well translated later into several stimulus, just to try that the circuit that you've been developing and you have inspect as the RTL or the technology view can be verified correctly, working as this table is stating, right?